The European Space Agency released their first images from the Solar Orbiter spacecraft. These are the closest images of the Sun ever taken and reveal details that have never been seen before. But though these images were only taken to test the spacecraft's instruments, they are already hinting at a possible answer to a mystery that has puzzled astronomers for over 150 years. Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. ESA's solar orbiter began its journey to the Sun when it lifted off from Cape Canaveral on February 9, 2020 at 11:03 p.m. local time. Its mission is to make the most comprehensive study of the Sun. It does this with a battery of instruments to study the Sun's atmosphere, corona, solar wind, and magnetic fields. Its imaging system has already provided the closest images ever taken of the Sun and will make the first ever direct images of the Sun's poles. All of this is critical for understanding how the Sun drives space weather and how solar storms directly affect our home planet. After separating from the Atlas V booster, Solar Orbiter deployed its solar arrays, antennae, and instrument booms. It then began its commissioning period. This is when the science instruments are turned on, checked out, and calibrated. Normally, this would be done with everyone working at ESA's Operations Center. However, the UK and most of the EU countries imposed strict stay-at-home orders early on in the outbreak of the novel coronavirus. So, Solar Orbiter became ESA's first spacecraft to be commissioned largely from people's homes. As part of its commissioning, test images of the Sun were made in May during Solar Orbiter's first perihelion, that is, its first close approach to the Sun. At the time, the spacecraft was 77 million kilometers away from the Sun, which is about half of Earth's distance. Even though these were just test images, they revealed details never seen before. These images were taken with the Extreme Ultraviolet Imager. It images the Sun's outer atmosphere called the corona. Throughout the images are what appear to be tiny flares dubbed campfires. These flares appear just beneath the corona. They seem like miniature versions of the larger solar flares that we can see from Earth. From this distance, each pixel corresponds to about 400 kilometers, so these campfires are still large by Earth standards. But the fact that they're showing up in these test images when the Sun is so quiet is quite surprising. You see, the Sun undergoes an 11-year cycle of magnetic activity. It starts out with a largely stable magnetic field, but as the Sun rotates, its magnetic field gets tangled, and this leads to sunspots, flares, and even coronal mass ejections. Right now, there's very little magnetic activity, so we are experiencing a quiet Sun. But these images show that even a quiet Sun is remarkably active, producing the same features we see during active periods, but on a much smaller scale. And like I said, these are just tests to make sure the cameras are working. They're not the science quality images that we'll get when Solar Orbiter gets closer. But these campfires hint at a possible answer to the mystery of the Sun's corona. Even though the corona is the Sun's upper atmosphere, temperatures there are about 1,000,000 degrees hotter than at the surface. And that makes no sense. That's like raising your hand away from a hot stove and suddenly getting burned. This phenomenon was first noticed in 1869, and scientists have been trying to figure out the reason for it ever since. One long-held theory is that there could be small nanoflares continuously erupting in the quiet corona. In the nanoflare hypothesis, local regions of the Sun's magnetic field become entangled due to convection in the Sun's surface. Electrically charged particles, or plasma, get trapped in the magnetic field lines. As the magnetic field lines become further entangled, they're squeezed together until they snap apart like rubber bands, unleashing a flare of energized plasma. This is called magnetic reconnection and is the mechanism at the heart of all explosions on the Sun. Individually, these small-scale reconnections are not significant events. Not a lot of energy gets produced. But the cumulative effect of maybe trillions of these things might account for the corona's 1,000,000-degree temperature. It sure looks like that's what's happening here, but just because something looks like what you expect to see doesn't mean it is. Even if the campfires really turn out to be nanoflares, it doesn't mean they're producing enough energy to account for the corona's temperature. It's also possible that these aren't nanoflares at all, but rather some other phenomena that mimics their appearance. Speaking of mimicking appearances, there's also what appears to be a giant tardigrade about two-thirds the size of Earth jumping around. And this is actually a defect in the EUI sensor. The reason it's jumping is because the original images were a bit shaky. The EUI team corrected this and stabilized the images, but now that the images are rock solid, the original defects of the sensor become shaky. Eventually, the EUI team will be able to further optimize their imaging algorithms and remove the defects from future images. But for now, we have a giant tardigrade and his buddies jumping around campfires. In order to find out what these campfires really are, Solar Orbiter needs to get a lot closer to the Sun. But getting there will take some time. You see, getting to the Sun requires getting rid of a lot of orbital energy inherited from Earth. To do that, Solar Orbiter will make a series of flybys of Venus and one flyby of Earth to dump orbital momentum and descend closer to the Sun. Eventually, it'll reach a closest approach of about 0.3 astronomical units in October 2022. There, the spacecraft will make its highest resolution images, as well as direct in situ measurements of the solar wind particles as they pass by. Additional Venus flybys will send Solar Orbiter to higher and higher inclinations above the ecliptic plane. That will allow the spacecraft to obtain the first direct images of the Sun's north and south polar regions. The only other spacecraft to fly over the Sun's poles was Ulysses, which was launched in 1990. Ulysses used a gravity assist from Jupiter to change its orbit and overfly the Sun, but it didn't carry any cameras. Instead, it made in situ measurements of the environment surrounding the spacecraft as it flew overhead. After 3 orbits, Ulysses was retired in 2009. Solar Orbiter won't directly overfly the Sun's poles because it won't be able to generate enough change in velocity with flybys of Venus. But it will be able to image the poles and study how the Sun's magnetic field converges there. Solar Orbiter is equipped with 6 remote sensing instruments and 4 in situ instruments. The Extreme Ultraviolet Imager images the Sun's lower atmosphere at ultraviolet wavelengths. This alone is a reason why we need a spacecraft in the first place. The Daniel K. Inouye Solar Telescope is the largest solar telescope ever built. When commissioned in 2019, it made the highest resolution images of the Sun to date, revealing details as small as 30 kilometers across. However, DKIST is underneath Earth's atmosphere, which blocks most of the Sun's ultraviolet radiation. In order to study the high-energy corona, we need to go to space so we can see at UV wavelengths. The METIS coronagraph images the corona by blocking out the Sun. It makes 2 images simultaneously, one in visible light, shown in green, and one in ultraviolet light, shown in red. The ultraviolet light is caused from emission by neutral hydrogen in the corona. The images show streamers emanating from the Sun's equator, which is pretty typical of the Sun during its quiet period. However, METIS captured even higher resolution images when it closed into 5.2 AU on June 21st. The heliospheric imager, or SOLOHI, images the solar wind by capturing the light scattered by electrons in the wind. This image is a mosaic from 4 separate detectors in the imager. The partial ellipse visible on the right is sunlight reflecting off the dust particles that are orbiting the Sun. This is called zodiacal light. The solar wind outflow is faint by comparison to the zodiacal light, but the SOLOHI team developed techniques to reveal it. The polarimetric and helioseismic imager, or PSI, measures the magnetic field near the Sun's surface. It also allows for the investigation of the Sun's interior via the technique of helioseismology. The PHI full disk telescope shows the Sun pretty much as it would appear to the naked eye, as long as it was wearing enough welding glasses. The lack of sunspots really shows how magnetically quiet the Sun is right now. PHI's high-resolution telescope reveals a magnetogram of the surface. The small structures seen here are magnetic regions with north and south polarities, some of which have sizes of a few thousand kilometers. From this data, magnetic field lines can be extrapolated into the Sun's upper atmosphere, which the EUI telescope images. The same region imaged by the magnetogram is shown here in visible light, which reveals the Sun's photosphere. The granules are the up and down convection cells of hot electrically charged plasma. Now that's just 4 of the 10 instruments aboard Solar Orbiter. 4 other instruments are in situ measurements to measure the magnetic field, sample the solar wind, charged particles, and radio and plasma waves. Now, these instruments will become very important when Solar Orbiter gets closer to the Sun. However, Solar Orbiter won't come anywhere near as close as the Parker Solar Probe. When Parker makes its closest approach, it'll come to within 0.05 astronomical units. It will actually fly through the Sun's corona. So it's natural to wonder why they didn't just put a camera on Parker to take even closer images. Well, it turns out that at 0.05 AU, the radiation environment is so strong that there is no feasible way to fit a camera capable of surviving those conditions. However, its WHISPER camera looks sideways to image the solar wind passing by. So the two spacecraft complement each other, each making different measurements in different regions.